Okay, now let's start. Today we will talk about polar coordinate. So polar coordinates is a name for 2D. In 3D, we have more choices as a cylindrical coordinates or spherical coordinates, which will be discussed later. So recall the following definition. So on this side, you have rectangular coordinate system, and on this side, you have the corresponding polar coordinate system. So the transformation law is given by the following. X is r cosine theta, y is r sine theta. And if you know x and y, then you can write down r is square root x squared plus y squared, and theta, actually you don't know exactly what theta is, but you know what is tangent theta. This is y divided by x. Usually here you need to determine theta, you need to make a choice depending on the quadrant. Where the point is. Okay, this is just a first recall. Next, let's turn back to the main topic, the double integral. So suppose now we have the following domain. So outside boundary is given by x squared plus y squared equals 4. Inside one is given by x squared plus y squared equals 1. Okay, if we want to calculate the area, then you see it's neither type 1 nor type 2. Therefore, you need to do the following cutting. So this is first cutting, then change to type 1 domains. You can do some calculation, or someone prefer type 2 domains. You can do the corresponding cutting here. Then you have 3 pieces. This one, and this one. So you have type 2 domains to help you to calculate the integral. Okay, but we know. So if you are satisfied with all this method, then we are done with this lecture. We don't need to do any more. But if you are not so satisfied with this, because you think the half annulus is a very good shaped domain, you expect a better way to understand the area, then we come to the following idea. If we change the domain D, so let's call this as D, from rectangular coordinate system to polar coordinate system. Then what do you have? So on this side, you still have this half annulus, but then on this side are theta. So notice that here x squared plus y squared equals 4, and therefore, and also this one is x squared plus y squared equals 1. Therefore, r is between 1 and 2, and theta is between 0 to pi. And then you can draw the picture here. So the red line becomes this one, and the green line becomes this one. And then you have, let me draw. This is the boundary here. So you have this boundary here. Pi, this is 0 pi, 0 0. This is 1 0, this is 2 0. Okay, now you have a very well-defined rectangle on polar coordinate system. So if you are ambitious enough, then you want to transform. If we can transform the integral from, let me call this as d prime, d to d prime in a certain way, I will not specify at this point, but this turns out to be very important in calculation. What is the way formulating the transformation? If we can transform integral from d to d prime, we expect simpler calculation. Okay, so that's our main idea. We need to transform. And then the question we have is, what is the transformation law? Okay, or in other words, what is the way we transform? And whenever you don't know how to do that, let's look at some easy example. So easiest example, so suppose we are integrating the constant function 1 over d. So in other words, we are calculating this guy, and the geometric interpretation of this integral is the area of d in xy coordinate system. Okay, now suppose d is small and defined by the following data. Theta is between theta 0 and theta 0 plus delta theta. R is between R0 and R0 plus delta R. And in other words, you may draw the picture like the following. So the angle here, recall that here we are still in XY plane. So the angle here is theta 0, and the angle here is theta 0 plus delta theta. Okay, and the length of the radial part here is R0, and for this part is R0 plus delta R. Okay, now we can approximate the area as following. So this one is approximately a rectangle, and then we can calculate the area of rectangle by the product of is two of the length of two sides. So this one is is R0 plus delta R minus, sorry, I might use the red pen. R0 plus delta R minus R0, which is delta R. Okay, and then what is this size? Notice that this is not delta theta, but delta theta times R0. This is a crucial point. Crucial. Okay, then here the area is approximately equals delta R times delta C0 dot R0. We can write down, sorry, here you don't have 0 here. You can write in the following way, if you want. Okay, then you see, let's compare the corresponding area in the OD star in the polar coordinates. So notice that the region you might have is this one. R0 plus delta R. Theta 0 plus delta theta. So the area of D theta is given by exactly delta R times delta theta. Okay, then you will see we can draw the following conclusion. The area of D in XY coordinate system is different from the area of its image D theta in the polar coordinate system. This is true, but actually we have better result. That if you look at the factor here, this exactly is the radius of the small, it's a coordinate for the small rectangle, or the polar coordinate, the radial part of the polar coordinate. Then we might write down it as following. So the area of D approximately R times area of D theta. So if you take the limit infinitesimal version dx dy equals r dr d theta. If you admit this, it's okay. And if you don't, we can draw some geometric proof for this formula in the following. So I just want to say, eventually we will use this transformation law. So this is transformation law. Okay. So as we said, this is the easiest case, but now let's do the general case. So suppose now you have a region in this shape. Theta is between theta 0 and theta 1. Sorry. Let me. Between alpha and beta. R is between A and B. So this alpha, theta equals alpha, theta equals beta. And R equals A, R equals B. And this is called domain D. So what is the integral of function f over domain D? Just remark, this is in xy coordinate. Okay, then the idea for the proof for the transformation is we cut the domain into small pieces instead of draw lines along x and y direction. We draw lines along the radius direction. Oh, sorry, my bad. The xy coordinate system goes this way. The origin is here. Go this way, and then also we cut it along the circular direction. So numerically we have the following cutting. So cut d into dij. So I is from 1 to n, j is from 1 to m, such that dij is defined by the region theta is between theta I and theta I plus 1. R is between Ri and Ri plus 1. And for simplicity, we can assume we denote by delta theta I, the difference between adjacent theta coordinates, and Rj is the difference between the adjacent R coordinate of the small curved rectangular. Okay, now recall the definition of the integral. This is approximately the summation of small Riemann sums. For each Riemann sum, you pick a point inside the small region, and then you calculate the product of the function value with area. So here the area is, let me first, dij. I'd better write in this way. Area of dij here. And then approximately by the previous case, the easiest case for small rectangles, curved rectangles, we had the following formula. This is Rj times area of dij. Okay, since we want everything to be in polar coordinates, so next we transform the corresponding points into its polar coordinates. So f ij star cosine ij star theta ij star, and here y is iij star sine theta ij star. And next you have this. So recall the area for delta ij is delta ij times delta theta I. And this, if you forget about all the information from x, y, then what do you have? This is exactly the integral over d theta of the function fr cosine theta r sine theta dot r dr d theta. Okay, noted that although you have a lot of approximation here, but the quantities on left-hand side and the right-hand side are exact. So that depends on how you cut in, how you choose a point xij star, yij star, rij star, theta ij star. So we can prove that the integral in polar coordinate system equals the integral of r cosine theta r sine theta times r d theta in the corresponding polar coordinate domain in the corresponding domain in the polar coordinate system. And as we emphasize again, here the most important thing is you have actual factor r here. Otherwise, the formula is not correct. Later on, when we introduce the Jacobi formula, we will discuss this discuss the transformation law for arbitrary transformation, but all of them have the same feature here. You have some transformation between the areas, and then the area and the transformation law depends on the exact form you have. Okay. Next, as soon as we figure out this one, then if you are ambitious enough, then you will probably interested in the following domains. Polar, type 1 or type 2 domain. So first recall what is a regular type 1 domain. So regular type 1 domain looks like this, and the regular type 2 domain looks like this. Okay, then for the polar one, what does that mean? That means in polar coordinate system, D star looks like type 1 or type 2. So in other words, suppose you have r theta coordinates, and then if your domain this theta looks like this, we call it type 1. If your domain looks like this, we call it type 2. And you might want to transform this into a rectangular coordinate. Then what does it look like? Then for this one, it's probably easier. For the first one, for the type 1, probably for type 2, actually it's easier. So let's see. So because your angle, so let's draw. So this is red, this is red, and correspondingly you have red here, and then you have green one. Theta. And mainly we will use the type 2. Okay, so here actually it should be type 2 corresponding type 1. Okay, those terminology are not standard. Type 2, type 1, type 2. It's not a standard terminology, but in this class we will use this for simplicity. And actually the key point is you understand what's the fundamental idea, what's the essential part. Okay, I leave it to you to figure out. Draw the corresponding picture here. Okay. So now let's derive the formula, integral formula for the for the double integral over polar type 2 domain. So suppose you have integral as following. D is polar type 2 domain. Then first we can use the general formula transform the type 1 transform the integral over xy plane to the polar coordinate plane. So this will be d theta f r cosine theta r sine theta r dr d theta. Okay, next we can use, so this step is transformation law between xy coordinates and the polar coordinates. And then the second step is type 2 iterated integral for type 2 domain. Okay, then here you can easily write down its integration from alpha to beta. So let's assume this is beta, this is alpha, and with respect to theta, and then integral of h1 theta to h2 theta. So let's call this boundary h2, this boundary h1. And then the integrand, you just keep it, because when you do the iterated integral, you do nothing to the integrand. So r cosine theta, r sine theta, r dr d theta, dot r dr. Okay, so as a conclusion, we would like to write the formula again. Of course, here D has certain special shape. Okay, next let's do some example. So find the area enclosed by one loop of the four-leaved rows r equals cosine to theta. So first, let's draw a picture. I think we draw this picture before. Okay, so let me think about. Okay. I hope you get the idea, but I would like to redraw it. Okay, so this is enclosed by 4-leaved rows, and then actually we are interested in only one leaves, so this part. Okay, so as you see, first we need to represent the domain D in the polar coordinates. Okay, so first we need to figure out what is the angle alpha and beta. So the geometrical meaning for the angle alpha beta is that they make R to be 0. Okay, so they make R to be 0. So set R equals 0, then cosine 2 theta equals 0, and 2 theta is given by pi over 2 plus k pi. K is 0, positive 1, positive 2, all the integers, and then theta is pi over 4 plus k over 2 pi. And in particular, you will have the following solutions near 0. And look at the picture, we know alpha is negative pi over 4, beta is pi over 4. Okay, therefore the area, first we use the geometric meaning for the area. This is an integral of 1 over domain D. Then we use when we use the formula here, we can write down as following. So as follows. So here you have integral from negative pi over 4 to pi over 4 with respect to theta, and then you have integral. Noted that here the region for R is between 0 cosine 2 theta, and then inside you have 1 dot R dr d theta. Now let's do the calculation. So we first do the R integral. So it's R squared over 2 cosine 2 theta 0, negative pi over 4, pi over 4. So cosine 2 theta squared over 2 d theta. And then we use trigonometric identity. Noted that here I would like to mention to you cosine alpha square equals 1 minus cosine 2 alpha divided by 2. So choose alpha to be 2 theta. We have the following. So this is 1 minus cosine 4 theta over 2, and then over 2 d theta. So this is integration of 1/4 minus cosine 4 theta over 4. So this is 1/4 theta minus sine 4 theta divided by 4 times 4, and evaluate at 2 endpoints. And here, notice that sine for pi over 4 equals sine for negative pi over 4 equals 0. Then actually you don't have this part. So the answer will be pi over 4 minus negative pi over 4, which is pi over 8. So Europe, now we know the area for this region is pi over 8, which is impossible by any formula we learned before. We just calculate by calculus. So we know something. Okay. Next. Let's do one more actual example. So find the volume of the solid that lies and the paraboloid z equals x squared plus y squared above the xy plane and inside the cylinder x squared plus y squared equals 2x. So we can draw the picture like the following. So this is a 3D picture. So this is x, y, z, and you have, so first, let's simplify this cylinder. If you complete squares, this looks like this, and then the cylinder has the following shape. Okay, next, what about the paraboloid? So the paraboloid looks like this. Okay, then the region we are interested in is this part. So underneath the yellow one, above the xy plane, inside the blue one. Okay, therefore, use a similar strategy. We may represent the volume of the red solid as the integral over domain D. I will figure out D later, but then inside is the height function. So first, let's figure out what is D. We project the red part to xy plane. Then you will see exactly the following picture. Okay, so this is our D. And what is the height function? So remember, the height function should be a function depending on x, y only. And then this will be the coordinates on the top minus the coordinates on the bottom. So this is a height function. So this will be, look at the formula we have here. So z coordinates on the top minus z coordinate on the bottom. Since the bottom is xy planes, which is 0, so we only care about the coordinates on the top. So this is given by x squared plus y squared. Therefore, here you have xy plus y squared minus 0, which is x squared plus y squared. Okay, now the volume is simplified to the integral of function x squared plus y squared over the domain D. D is here. It's not so easy to calculate because instead of, you can view it as type, you cut it in two parts. For example, in this way, you have two type 1 domains, but then problem is the boundary is a little bit hard to describe. So this boundary, green boundary, is a little bit hard to describe because you have to take roots. Okay, instead of this, okay, so method 1, I would like to introduce a method 1, cut into two type 1 domains and calculate. And the second method is, we already recognize this is a disk, although it's shifted by 1 in the positive x direction, but it's still a circular shape. Then we think about using the polar coordinates. We need to transform the domain into polar coordinates. So the domain is given by x squared plus, so the function is here. So x squared plus y squared less than or equal to 2x because you are inside the disk. Then if you transform to polar coordinates, you have the following equation. Or equivalently, you have this one and same as r is between 0 and 2 cosine theta. And notice that here you have some region for your angle theta. So the angle theta will be between pi over 2 and negative pi over 2 from the picture. Or you can solve the equation r equals 0 as before. You can derive theta is negative pi over 2, pi over 2, and shifted by k pi. So we choose the closest two solutions according to the picture. Okay, then the integral now can be written down as iterated integral as following. Theta is from negative pi over 2 to pi over 2, and then r is from 0 to 2 cosine theta. And inside, we substitute x to r cosine theta, y to be r sine theta. Okay, so here I almost make a mistake. You have r dr d theta. This r is important. Okay, now we simplify the integrand. This is r cubed dr d theta. And then we integrate using power rule. We get this one. So you plug in, you have this. We can simplify a little bit, get rid of the denominator. So you have 4 cosine theta to the 4th. Now we use trigonometric identity again. 4 cosine theta square. So for cosine theta square, we use the identity 1 minus cosine 2 theta. And then simplify a little bit. Actually, you can do distribution law. It's 1 minus 2 cosine 2 theta plus cosine 2 theta square d theta. For first two terms, we are in good shape. For the last one, we use the trigonometric identity again. This is 1 minus 4, cosine 4 theta d theta. And we collect terms. We have 3/2 minus 2 cosine 2 theta minus 1/2 cosine 4 theta d theta. Okay, then we can do the one variable integral minus 1/2 1/4 sine 4 theta. So the point is pi over 2 negative pi over 2. And also here, notice that sine 2 theta, sine 2 pi over 2 equals sine 2 negative pi over 2 is 0. And the sine 4 pi over 2 equals sine 4 negative pi over 2 equals 0. Therefore, you don't have this, and essentially you have 3/2 times pi over 2 minus negative pi over 2, which is 3/2 pi. Okay, I will stop here for the polar coordinates. Next time we will discuss some application and of the double integral and start the triple integrals.